That axial force, so 40 kilonewtons on each side, which I'll put in base units. So thinking about the equations we just saw in the materials section, what else usually appears in these equations? Or looking at what's in the diagram, what else do we need to know?
The delta for the length for the strain and length is 3 millimeters.
Right, it elongates by 3 millimeters. So that was the linear deformation, which we denoted as little delta, is 3 millimeters. Or 3 times 10 to the negative third meters is the elongation or change in length of the rod. Right, we will need the area. I'll start by the things we're directly given. We're given, to find the area, we are given the inside radius, which is 10 millimeters. So I'll call that R sub I. And the outside radius was 12.5 millimeters. Right, the initial length, the pictures we're given are almost always the kind of when it's just resting there before we're loading it, and then we put the load on, and then it deforms. Originally, this rod is 0.9 meters long. Right, we're told that the circumference decreases by 0.09. I'll call that delta C for this problem. It decreases, that's going to be negative 0.09 times 10 to the negative third meters. And we want to find the modulus of elasticity, the Poisson ratio, and the shear modulus. We want to find E, nu, and G. We're using stresses here, or things are derived from stresses. I do want a free body diagram. It will be very simple. What do they call it? I'll call this F, so we don't confuse it. The internal load is P. Obviously, it's going to also be 40 kilonewtons, but we still need the free body diagram to show that that's true. Internal force, 40 kilonewtons, or 40 times 10 to the third newtons, and it's in tension. Now we have the internal force. Now we can proceed with the rest of what we want to do. So we have a lot of information, a lot of things we need to find. How can we use those formulas we've been using to solve for the material properties that we have here? I would suggest starting with is we can use this relationship right away. The other ones are also fine, but this will, for right now, we don't have to find the stress directly. We don't have to find the strain directly. Right now, we know all of the things in this equality except for the Young's modulus. So this right away will give us that Young's modulus. We know that delta was 3 times 10 to the negative third meters in base units. Internal normal force is 40 times 10 to the third. The gauge length, or the unstretched length, was 0.9 meters. Young's modulus is what we want to find. And the cross-sectional area of a ring will be pi r outside squared minus r inside squared. The outside radius was 12.5 times 10 to the negative third. And the inside radius was 10 times 10 to the negative third. From this equation, again, the only thing we don't know is the Young's modulus. And we can get the Young's modulus out of this then by solving for it. The Young's modulus of the material, 67.9 gigapascals. Actually, let me back off since we haven't used gigapascals yet. We get 67.9 times 10 to the 9th pascals. A billion pascals, or a billion of anything, is a giga. So this is one way of finding the Young's modulus. Again, we could have started by finding the normal stress, the normal strain, and then related it separately. This did it all in a single equation. By definition, the Poisson ratio, I'll write it up again. In shorthand, it's negative the ratio of the strain in the unloaded direction to the strain in the loaded direction. Neither of which do we know at the moment, but we will be able to calculate them. The loaded direction, I don't have the full picture up here. It's being loaded along this axis, so the unloaded direction will be the radial direction. So if we can find the strain this way, if we can find the strain along the radius, we'll be able to find what the Poisson ratio is by dividing the two and negating it. So let's start with the easier one. How can we find the strain along the loaded direction?
Delta over L naught.
Right. It's a normal strain, and Tyler brought it up before, or someone said this one before. We do know both of these things, so we can calculate the strain along the loaded direction, or what I called already the x direction. The change in length was 3 times 10 to the negative 3 meters. The gauge length was 0.9 meters. So the normal strain along the loaded direction is 3.33 times 10 to the negative third millimeters per millimeter. This gives us the denominator, and just so it's clear, it's positive, it's elongating. We have a positive strain. How are we going to find the strain in the unloaded direction, which is going to be the strain in the radial direction? This one's going to not be quite as easy to begin with. What we will get to is the strain in the unloaded direction. If we know the change in the diameter or the radius, it will be the same ratio. We need to find this. The change in the radius over the original radius will be the strain along the radial direction. Well, we know the original radius. We want to be a little bit careful here because it's hollow. Look at the information they gave us. Where did it go? The outer circumference decreases by 0.09 millimeters. A little bit of the notation here. This is meant to be the gauge radius, but I actually will be using the original outside radius here. I could also do both of this with the inside radius, but it'll be harder because I don't know the change in the inside radius. It'll be easier to find the change in the outside radius since I know the outer circumference and how that changes. So the denominator will be the original outer radius, which was the 12.5 millimeters. The change in the radius will be the loaded radius, outside radius, or the new radius, minus the original divided by the original. We know that the change in the outside radius, it decreases 0.09. That was information that was given to us. Millimeters. That's the change in the outer circumference. So that's going to be the new circumference, which is 2 pi r prime, I'll call it, minus 2 pi times the original radius, which was the 12.5 times 10 to the negative third. The only thing I don't know, I'll accentuate this as negative, the circumference decreases, therefore the new outside radius is smaller than the original outside radius. If I solve this, the new outside radius is 12 point, I'll have a couple of decimal places here because the differences are usually pretty small. The new radius with 5 digits of precision, 12.486 times 10 to the negative 3 meters. I know the new radius based on that change in circumference information. I know the original. Now I can find the strain in the unloaded direction or in the radial direction. By doing this calculation, I get that the strain in the unloaded direction, negative 1.12 times 10 to the negative third millimeters per millimeter. We'll check the signs here. This elongated for almost all materials. If it goes larger in one direction, it gets smaller in the other. So we should expect this to be a negative value since the radius is going to shrink a little as we pull the material apart. We now calculated the loaded strain, the unloaded strain. We can calculate the Poisson ratio by dividing the two and negating it. 1.12 divided by 3.33 is going to give us a Poisson ratio of 0.336. We have the Young's modulus, which I erased, but I'll put back up here. From the first step was 67.9 gigapascals. We have the Poisson ratio, the last thing we need. So this is done. This is done. How can we find the shear modulus, G? Right, we can use the relationship we have between these three material properties, shear modulus, Young's modulus, Poisson ratio. Only two of them are independent. If we know two, we know what the other ones are. For any material, this relationship is going to be true. We aren't told any information about shear, which is where experimentally we can determine what the shear modulus is. But because we know these two things, we can figure out the shear modulus this way. So because we did the first two steps, we now have all the information we need to solve for the shear modulus. We get a shear modulus 25.4 gigapascals.